Hello, and welcome back to the Mathematicians Podcast, the show where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we're travelling on the road less taken, or perhaps that should be most taken. It is possibly one of the most famous roads in the whole of history, even if so few people take it. I suppose, in a sense, this is yet another road that leads to Rome, although less directly, as this artery connects India, China, and Arabia. Oh, go on then, have a think to yourself. How many famous roads could you actually name? There's the Telegraph Road, Abbey Road, Country Roads Take Me Home. I am, of course, talking about the Silk Road. So, who is our traveller today? Well, today we are discussing Yavanesvara. But first, actually, before I jump into the section of script marked Intro Ramble, let me give you a quick update from me. Baby Cornish was born healthy and happy, and we've been doing great. She's actually asleep on me right now, hence the different sound quality. I've had a really good month away from writing, as the last 3 episodes were pre-recorded, but ready to get back to it. So, what happens next? Well, I could either sacrifice the speed of delivery for future episodes, or sacrifice the quality of research and writing. And based on the timestamp of this episode, I think you can guess which way I'm going to go with that. In case you haven't noticed so far, with the exception of a few really famous people, like maybe 10 out of the last 50, I know next to nothing about the people I cover before starting each episode. I'm not an expert on history. It's a learning journey we are on together. As such, I feel it would be personally disappointing for me if I didn't try to understand what the people were really about at this time, what the impact of their contributions were, or how cool the maths really was. After all, I research it for my own amusement. I just write it down and record it to give me a reason to do so. So, episodes are going to come out more slowly, but hopefully still be as deep and fulfilling. And for those of you listening years after I stopped publishing, you won't notice the difference. Also, hello, from the year 2026, we still have running water and occasional snow. And if you still use currency when you're listening to this, feel free to chip in a few coins to my Ko-Fi account and help me pay for my daughter's first trike or car, university, or the grandkids' wedding. Delete as applicable. Okay, on to the story of Yavanesvara. But first, when I was a younger man with nimbler fingers and keener eyesight, I used to run a gem shop near the beach on the South Dorset coast. Dorset's north coast is famously far away from the seaside. Lyme Regis is a beautiful town with an abundance of interesting geology. Folding rock strata, a high prevalence of marine fossils, from tiny ammonites to sprawling sea monsters. It even has the same shale oil field that runs underneath the UK and re-emerges in the North Sea. Down here in Dorset, though, we don't crush our fossils up into goo and burn them in cars. Instead, we extract the fossils carefully and sell them to children and weirdos. Now, as any geologist can tell you, lime sits on layers of limestone. Dorset is famous for it. Sadly, any etymologist can tell you that lime does not share its name with limestone. For audio listeners, Lyme Regis is spelt Lyme, and this comes from the Celtic word for the river Lim, where the town sits, and Regis because it was once visited by the king, whereas limestone comes from an old German word meaning sticky. What makes the geology sticky is that limestone, CaCO3, is a form of calcite, which is great if you want to find deposits of alabaster or selenite or quartz or pyrite, but you can't make a gem shop with just these local crystals. Actually, that's not wholly true. I'll share a small trade secret with you that many of the less reputable gem shops in the area run almost exclusively on quartz. Rose quartz, tiger eye, agate, amethyst, jasper, all quartz. But kids these days don't just want quartz. They want exciting minerals like turquoise and obsidian. Have you ever tried finding turquoise in the UK? I mean, sure, there's some scant deposits in Cornwall. Of course, serious gem heads would want their turquoise to come from Turkey. But the folksy tourist trade that I catered to took most of the minerals from Mexico. Which raises the question, What's the point of having a location-specific shopping industry, that is, a rock shop in Lyme, if most of the really good stuff is shipped in from abroad? Well, as an old shopkeeper who hung up his hammer years ago, I can tell you, sometimes foreign rocks are just better. So far, in the Mathematicians Podcast, we have focused on mathematicians whose names we know. Today, we place a toe outside of that circle. History knows his name as Yavanesvara, but etymologically, this translates as Greek Lord, or perhaps Lord of the Greeks. It's more of a title, possibly a job description, more so than a given name, or at least we now believe. The Yavanas were a community of Greco-Indians living on the west coast, who frequently travelled to and from Greece and India for trade. Many members of the community would have been ethnically Greek, although fully Indianized in custom and tradition. Occasionally, I find myself doing research on this period of history, and I get surprised at how ethnically diverse communities are. But then I remember that race is a made-up concept that has only existed for the last few hundred years, and I get on with my day. Yavanesvara, however, that being the Lord of Greeks, was a rank of a civil servant who oversaw the community of traders. The specific Yavanesvara that we are interested in today came from the city of Ujjayini, modern-day Ujjain in Madhya Pradesh, and worked under the rule of the great king Rudraman I. Whilst we're discussing ethnic diversity, it might be interesting to note that this kingdom originated from the nomadic tribes of the Eurasian steppe. It was also this group that became major patrons of Sanskrit, with Rudramadam's rock inscription being one of the earliest examples of classical Sanskrit. It's a record of water management, really flowing text. I feel like I say this most episodes in the series on Indian and Persian mathematics, but I would like to insist that we don't continually discuss the mathematics of ancient India in relation to their Greek contemporaries. It's a sad legacy of Western exceptionalism to presume that all knowledge must have stemmed from Greece. However, today we're going to be explicitly discussing the knowledge that stemmed from Greece. The trouble with Greece is it just spreads everywhere, but at least it allows for frictionless transmission. Now, at the top of this episode, I discussed roads, in particular the Silk Road, and I imagine that you're expecting something made out of gravel and compacted mud that goes over mountains and across plains. Indeed, there was a road that connected North India, China, and the Eurasian steppe and into Arabia. But the trouble with this passage is that Persia and Rome are constantly at war. So any traders wanting to share goods and wealth with the Roman Empire passing through Persia will have to pay a heavy duty. Fortunately, a second Silk Road opened up along the sea with the discovery of the monsoon winds. From June to September, as the Asian continent heats, a massive low pressure zone is created. This draws the moisture-heavy air away from the cooler ocean towards the land, blowing consistently from the southwest to the northeast. But then from October to February, the land cools down quicker than the ocean does, and it makes a high-pressure zone, and the wind direction flips. Rome lives in the northeast, India in the southwest. So goods travel from all over the Roman Empire to Alexandria, down the Nile or up the Nile, depending on your perspective, a short land crossing from the Nile to the Red Sea, and once you're in the Red Sea, you can go around the Bab el-Mandeb Strait, a choke point that was just as politically sensitive then as it is today. You just had to hope that the local powers like the Himmerite Kingdom weren't being encouraged by Persia to cause trouble for Roman merchants. Funny how some things never change. And then after that, it's a quick 40-day travel to the coast of India. Remember that before this discovery, ships would have had to have followed the coast, which would have taken several months. Open sea sailing is fast, but it can be dangerous. Many ships would be lost, and lots of merchants didn't come home to their children. But to give you an example of why people made the crossing, you can consider a peppercorn. In the markets of South India, a kilogram of pepper would have cost you about 1, maybe 2 hours of labour. When it arrives in Rome, you could expect it to be maybe 2 weeks' worth of labour. By the time that kilogram of peppercorn makes it to the frontier in Britannia, it costs roughly 2 months of a soldier's salary. You might say that the cost of living has always been lower in India compared to the UK, but the scale here is incomparable. For reference, the current median salary in the UK is approximately 10 times higher than that of India, whereas ancient peppercorns were 600 times higher. Luckily for modern economic historians, Pliny the Elder famously calculated the trade deficit from the Roman Empire to the Indian merchants, suggesting that 100 million sesterces were leaving the empire every year to pay for Indian goods. Whilst researching this, I had a lot of fun trying to figure out how to put that figure into modern terms. If you take the pure silver content of the sesterces and melt them down, then under today's prices, it would be $265 million. If instead you look at the daily pay of a Roman soldier and assume that the nearest comparison today, that being the Swiss Guard and the Vatican, should expect the same pay, then you can find the buying power, which is about $2 billion. If you perfectly preserved the coins and sold them for the current auction price of a sesterce to a collector, it would be $86 billion. Now, silver prices fluctuate up and down, and the coins would be worthless if we'd preserved so many of them, so I think the $2 billion is a good value. Today, the trade value of the EU with India is about $120 billion. Luckily, we don't still haul it away in kilograms of silver. So, the maths of economics is fun, but that's not why you tune in. Let's get back to Yavanesvara. The city he worked in, Ujjaini, was a centre of astronomy as well as trade. Indian astronomers and map makers used it as the prime meridian, that is, the zero longitude. This is the line running from the North Pole to the South Pole, or if you're a map maker, from the top of the page to the bottom of the page, or if you're a flat earther, from the centre to the great ice wall at the edge. Yavanesvara is primarily known for one piece of written work, semi-original, the text called the Yavanesvara. It's primarily a work of translation from the Greek masters of horoscopy, so sadly not exactly a maths book, but an instructional guide for astrology. But before we question too much why it's included in this series, let's consider what the implications of this book were. Yavanesvara took the teachings of the Greeks, transported across the sea road and collected from his merchants. He translated the teaching into Sanskrit, but also reframed the concept of astrology into an Indian worldview, replacing the Greek pantheon with the Hindu pantheon. We also see a more systematic change to astronomical measurements. For instance, prior to Yavanesvara, the zodiacs were split into 27 constellations. This is called the nakshatra system. But we now have a 360-degree reference frame, and we also make use of the 12 signs of the zodiacs from the Greeks, including some delightfully phonetic loanwords from the Greeks. For instance, Aries in Greek is krios, and in Sanskrit it's kriya. We've talked before about base systems and counting, so I hope the advantages of this become obvious. You can divide the circle of the night sky into as many positions as you like, but there's only a few factors of 27 for division, whereas 360 would allow for much more precise measurements. Alongside this cultural shift, we see a major mathematical tool travelling from Greece to India through Yavanesvara. I'm talking trig tables. But if you thought this episode was going to be entirely a case of didn't the Greeks do everything first and better, then I'm afraid it's time for the tables to turn. You might recall from our discussions on Ptolemy that trig tables in the Greco-Roman world focused on the chord. So imagine you're looking at a star in the night sky. This star sits on a great circle with you at the centre. You can then draw a straight line in front of you, stretching off until it hits the great circle. This would be the radius. Another radius of equal length stretches up to hit the star. Connecting then the star and the horizon gives you a chord across the surface. What Ptolemy collected was a set of lengths of these chords for any given angle at the centre. if you were interested in calculating the time of the night, or perhaps a measure of latitude or longitude, you might want to know how high above the horizon a reference star might be, which you could then either calculate directly or compare against a reference table to make a calculation. But the Indian mathematicians, following in Yavanesvara's wake, noticed that Ptolemy's method have a clunky unhelpfulness, and that we are less interested in the distance between a star and its vanishing point on the Great Circle, and instead we're interested in the vertical height above the diameter. In order to correct this, we need to draw our chord differently. Rather than connecting the star's position to the horizon, we can drop a vertical line from the star's position to a flat Earth. However, if we were to measure the angle between the Earth and the star's location, this would only represent half of that total chord, and thus we have invented the sine function. Remembering that the sine of an angle is the ratio of the opposite divided by the hypotenuse on a right-angled triangle, the hypotenuse is the constant radius of the great sphere, and the opposite is the height above the horizon. Although, of course, that was not how the Indian scholars treated the sine. So, no, not all the maths in today's episode was invented in Greece. The possibly most useful function of all mathematical history was born at pretty much this moment in India. The signs were there all along, but it takes a traveller to know the journey. When this version of trigonometry passes back into the now very Christian-dominated Greco-Roman world, they considered that the Hindu measuring system with half the chord was a sin. Go on then, another quick etymology lesson because I find it fascinating. The Sanskrit word for this trigonometry was jya, which translates to bowstring. The word we use today is sine, from the Latin sinew, which are the stringy tendons of animals that we use to make the bowstrings. And if you draw a circle, drop a vertical chord and connect the two radii to the ends of the chord, you'll see that you have effectively a bow and arrow being drawn, by which I mean it's been drawn and drawn. I don't know how to make that particular pun more clear. Now, I really like that etymological description, and if I'm honest, it's been the one I've been using in my classroom teaching for about 10 years, hence why I wrote it down today. Sadly, upon double checking, I realise it's not actually correct, although the true etymological chain is also interesting. So we have the jya from the Sanskrit bowstring, which transliterates into Arabic jiba. Somebody somewhere misread jiba as jayib, same letters, different arrangement, and this time it means to fold. And then the Latin word for folding is sinus, and that's where we get the word for sine. I think it's delightful, though, that the folding also feels an appropriate term to measure the sine, given that the chord is folded in half. Sadly, the word sinew for bowstring actually has no etymological link, coming from an old German word to bind or twist threads. Maybe twisting is a type of folding? Pleasingly enough, sinus could also refer to a curved cavity, especially in the body, much like a curving, twisting tunnel. And I've fallen much too far down this particular etymological turning, twisting tunnel. Gosh, sorry about that. Right. Well, now that we have a method of using vertical height to calculate the angle, it becomes easier to associate a star's position in the sky with a time or angle. The first task, then, would be to use a vertical rod of known length and then find the position on the floor such that the tip of the rod lines up with the star or planet. And you now have the opposite and adjacent lengths of a right-angled triangle. So, using Bauthian's theorem, or if you prefer, Pythagoras' theorem, you can calculate the length of the hypotenuse. From there, you can look it up in your table of sines to calculate the angle. So, why bother measuring two lengths and then using two calculations for an angle? Why not simply line up a sight tube with the star and calculate the angle with a vertical ruler? Well, I'd suggest you try doing both methods yourself and see which gives you a greater level of accuracy, assuming that all you're allowed to use is a centimetre ruler. Now, I like to joke a lot about flat earthers, although this is a relevant and serious point of discussion. If you are simply measuring the angle of a planet in the night sky, it doesn't matter whether the Earth is round or flat, because in the local space, it is flat. Personally, I believe the Earth is flat over here in the UK, although it's flat in a different direction over in Australia. Actually, that said, I went to university in Wales, where it is anything but flat. But what if we want to use trigonometry and the angles of stars and planets to calculate where we are in India? If you were to measure the sun at its peak in the sky, you could calculate the angle of that point, and this is called the meridian transit. At the equator, this should be directly overhead. But if you move towards the poles, the angle decreases. This is strong evidence to reject a flat Earth. Comparing the north of Greece with the south of Greece, the difference in the meridian transit is approximately 3 or 4 degrees. If instead we look at North India and South India, the difference is closer to 29 degrees. So that means the lookup tables for the sun's angle and how it relates to latitude need to account for this curvature. I should point out that the measurements we've described above can be accurate down to about 30 arc minutes, or half a degree. Obviously, the modern system we use to find our exact coordinates via satellite and a GPS system, and that gets precision down to a fraction of a milliarc second. If the Earth were flat, then measuring the latitude would simply be a distance from the equator. We'd end up with a relationship such as tan of the angle of the sun at noon, calculated with a vertical stick, and measuring the shadow. This method relies on the sun travelling vertically above the equator of the flat Earth, and it mostly works because, as I said before, the Earth is kind of flat close to wherever you happen to be. To put this into perspective for you then, for your latitude error to be greater than 1 degree on a curved Earth, you'd need to be about 3,000 kilometres away from the equator. Is that a lot, I hear you ask? Well, the total distance from the equator to the North Pole is 10,000 kilometres. Well, actually it's 10,002 due to a measurement error by the French, which I cannot wait to talk about one day. Yavanesvara can do better than this though, and give you the latitude on the spherical Earth as an angle, or rather as a sine of an angle, using the definition of sine being the opposite over the hypotenuse. For this, we map the equinoctial shadow. Now, if you place a vertical stick on the ground and draw a line at the tip of the stick's shadow, you'll notice it draws a curve as the sun moves throughout the day. Where the shadow is shortest at noon and longest at dawn and dusk. What you might not have noticed, though, is that the trace of this tip is either concave or convex, depending on if it's summer or winter. The most curved version of this tip's path being at the summer or winter solstice. However, during the equinox in spring or autumn, the path of the tip of the shadow is a perfect east to west straight line. You can then form a right-angled triangle with the equinoctial shadow, and that gives you the sign of the angular latitude. Now, if we're doing some more advanced level astrology, it's not good enough to simply say where a planet is in the sky relative to me. We might want to know which city is this planet currently over. In other words, we might be interested in calculating the planet's longitude relative to the zero meridian line. This is where the mathematicians, following on from Yavanesvara's work, really caught the ball and ran with it. By firmly asserting a spherical model of the Earth, we can map 3 points in the night sky to form a spherical triangle on the surface of the Earth. Let's consider the location of the North Star as the point that is vertically above the North Pole. We consider our own location as the second point on the spherical triangle, and we draw a straight line from a planet that we are looking at down to the centre of the Earth to discover which city currently sits underneath, say Venus. From these 3 points, we can measure the hour angle, which is a measurement of the time of rotation of the planet relative to the Earth. In other words, the angle from us to the North Pole to the planet. We can measure our own latitude, now that we have calculated it previously, and we can measure the declination of the planet, that is, the angle between the planet and the North Pole. and incorporate those three angles into the astronomical triangle altitude formula, an application of the spherical law of cosines. So this is the sine of the altitude is equal to the sine of the latitude times the sine of the declination, plus the cosine of the latitude times the cosine of the declination times the cosine of the hour angle. I found this part of my astrology research frustrating because after I'd finally understood what all of those angles referred to, I sat back and thought, surely all we've done now is calculate the altitude, which we could have done using the gnomon and shadow trick. So later that night I went out to try and measure the shadow of the planet Venus, and that's when I realised the beauty of the spherical law of cosines. For those of you who missed the joke, you cannot measure the shadow of Venus at night. Now, generally, I find astrology to be quite silly, although, of course, I do follow all of the teachings and practices just in case it turns out to be true. I'm a skeptic, but I'm not that brave. But as a mathematician, what I can appreciate is what the ancient Indian mathematicians were trying to achieve. They felt it important to know exactly what planet or constellation was above the horizon precisely at the time of somebody's birth. As loyal listeners to the show can probably guess, I am a Taurus on Gemini rising. According to the trusted source, astrosofa.com, I am the curious and patient solid rock. This combination lightens the Taurus down to Earth's personality, which can be very serious at times. But remember, the celestial sphere rotates in one direction, the Earth rotates in another direction, and the ancient Indian mathematicians wanted to find the precise intersection of these two non-orthogonal rotating spheres. That would be easier if the divine creator gave us a flat Earth, as our zodiac signs would be equally spaced out and at right angle ascension, but Yavanesvara and crew considered the tilt of the Earth with a latitude of the observer, the obliquity of the ecliptic, and then used that to measure the oblique ascension. In the post-Yavanesvara age, we have a formula in the early Siddhantas to get a correction of these ascensional differences. So that is the sine of the difference is equal to tan of the latitude times tan of the declination. We can combine this with a table of standard rising times from our handy birch bark pamphlet to calculate the expected rising time of any given zodiac at any particular point on Earth. So, to make this make sense to you, I might give you an example. Consider you're in the city of Ujjaini, trying to predict the rising time of Aries. You know that it should take precisely 2 hours, as the 12 zodiacs are equally spaced over the 24-hour day. But the ascension time of Aries is actually 112 minutes, due to the obliquity of the ecliptic. Then after that, we know that Ujjaini has a latitude of 23.2 degrees, and the declination of Aries is 11.5 degrees, and that's around 30 degrees into Aries. So taking the arc sine of the tan of the latitude multiplied by the tan of the declination gives you about 5 degrees, and we know the Earth rotates 1 degree every 4 minutes, so that's a 20-minute correction. This gives you a real-world measurement of the time it takes for Aries to rise above the city of Ujjaini of 92 minutes. If you did the same measurement of Virgo, it takes maybe 205 minutes. So tell me again that the Earth is flat. Go on, I dare you. I might point out here that I've presented a bad modern reconstruction of ancient thinking, a bit like writing Shakespeare in text-speak. So please take this with a big pinch of salt emoji. And all of this is done without ever treating the sky as something governed by a single explicit equation. Instead, it's a system of geometry, corrections, and very carefully maintained tables. But whilst the mathematicians of this time were very comfortable calculating with sines and indeed cosines and tangents using the trig tables they devised, and even as they were able to correct their astronomy down to exacting values by considering the latitude and longitude, there is still something they can't explain. Have you ever noticed that the sun moves across the sky 1 degree every 4 minutes? Or perhaps you'd only ever really thought about that when I mentioned it a few moments ago. The trouble is, have you seen how long it takes for the sun to set? Easily the best version of the sun is when it glows orange and red and throws its purple and pink streaks across the heavens. And the travesty is it seems to disappear as soon as it becomes beautiful. This is not a trick of your mind because joy is fleeting and the world is cruel. Rather, it's a trick of atmospheric refraction in this cruel world. Because of the atmosphere being thicker at the point of sunset, the light is refracted or bent to make the sun look as though it's in a different place. This is the same principle as when you stick a pencil in half a glass of water, the pencil seems to be broken. The atmospheric refraction has two key properties. First, it breaks up the blinding white light of the sun into an array of rainbow colours, and secondly, it slows down the sun before it approaches the horizon, and then speeds it right up as it passes over the horizon. The mathematicians of Yavanesvara's time noticed this. They realised their calculations and theories didn't line up with reality. But this is where we have a moment of inspirational genius. Rather than throwing out their carefully curated theory, we have possibly the first known example of a recognition of observational error. They spotted the problem, they realised their numbers were wrong, and they developed useful corrections. Rather than throw the baby out with the bathwater, just notice the difference and enjoy your bath. This might seem like a small thing, but a recognition of observational error made for a useful tool in the theory of Indian science going forwards. As we round off for today then, it might be worthwhile noticing who exactly we're talking about here. I've pinned this episode on the single figure whose name we don't quite know but history calls Yavanesvara. But once again, this is not the work of a single person. Rather, he represented a broad movement in the development of Indian mathematics, something that neatly fills the time gap between the 800-year stint of Jaina mathematics, represented by Umaswati, and our next big heavyweight, Aryabhata. But more than just the team surrounding Yavanesvara, I wondered if it might be a good idea to look at what the merchants were doing around this time. When we think of mathematicians of the age, we're often drawn to those that discovered gigantic truths, or pushed the format and philosophy of number. But in truth, merchants and politicians were dealing with micro and macro economics all the time, and their contribution formed a more culturally dispersed relationship with maths. I will share two such examples of mathematics in the merchant community. There is no specific reason why they fall under Indian mathematics, more so than Chinese, Persian, or Greek. Ultimately, merchants are citizens of the world. At least the successful ones are. There's also no specific reason to discuss these methods today, as we don't have a firm time that we can point to and say, this is when it was invented. But an episode dedicated to merchants, feels most apt today. Firstly, I would like to share with you the idea of the double false position. We think this was in use before written mathematics, so prior to Ames in episode 1. Let's pretend that I'm still a merchant of gems and fossils. I get a new batch of 30 gems and 40 fossils, and I don't know how much I should sell each for. I paid the gem and fossil factory £300 for the whole batch. So I'm going to start by assuming that a gem should cost £5 and a fossil should cost £3. So I have an error of £30 because 5 times 30 plus 3 times 40 is 270. If instead I guess that the fossil should be £4 and the gem is £5.50, well, that gives me a total of 325, so my error is 25. We can then use a process that today we would call linear interpolation to calculate the true value based on the errors found. Let us focus on gems. my first guess multiplied by my second error plus my second guess multiplied by my first error, all divided by the sum of errors. So that is 5 times 25 plus 5.5 times 30 divided by 25 plus 30 is 5.27. You could use the same method, or just this solution, to calculate the true price of a fossil, which is £3.55. So now that I have calculated these costs to the nearest penny, I can confidently charge £30 for a fossil and £40 for a gem, knowing that I'll be able to pay off my crippling business loan from that ice cream van. As I say, this process is well known by this stage in history, and its author is now lost to time. But I think it's good to reflect sometimes on what daily mathematics might have meant to the people we're learning about. So I shall give you another example of what might have been common for merchants, although this next example can be more precisely linked to this period of history. It relies on a base 10 repeated numeral system, which only recently emerged in India under the Jaina tradition. It has its first pseudo-references in the Indian mathematician Brahmagupta in about 600 CE. It's evident in the workings of medieval European and Islamic merchants, and is first explicitly described by Fibonacci in Liber Arithmetica. So I'm going to say that it's post-Jain but pre-Brahmagupta, which means I can say with some confidence that we should talk about it today. It's known as casting out nines, and it's a method of checking one's account to find possible error. Not unlike how the final digit on your credit card number checks to see if you've entered in the previous 14 digits correctly. Hey, post your credit card number and security code into the comments below. Oh, actually, that could put you at risk of a scam. If you go to my Ko-Fi page, you can check if your credit card number is valid by sponsoring this episode. The way the method works is by taking advantage of modular arithmetic, specifically working in Mod 9. Because modular arithmetic is congruent over multiplication and addition, we can simplify larger numbers into smaller ones. So just to explain a bit about this idea, modular arithmetic says that all numbers are equal to their remainder when divided by n. For instance, 7 mod 3 is 1, because we can take 3 away from 7 twice and are left with 1. If I count to 10 in mod 4, it goes like this: 1, 2, 3, 0, 1, 2, 3, 0, 1, 2. So if modular arithmetic is congruent over addition, it means that a plus b mod c is a mod c plus b mod c. Or in multiplication, a times b mod c is a mod c times b mod c mod c. So for instance, we know 7 times 8 is 56, but 7 times 8 in mod 3 is 2. And also 7 mod 3 times 8 mod 3 is 1 times 2, which is also 2. So the way the ancient merchants checked their arithmetic was to apply a digit sum, that is, add all the digits together repeatedly and then check the same thing for the answer column. Imagine, after trading in my fossil and gem shop, I sell 4,675 gems at £40 and 3,382 fossils at £30, so I think the total was £213,460. But let's check those numbers. 4 plus 6 plus 7 plus 5 is 22. 2 plus 2 is 4. 4 plus 0 is 4. 4 times 4 is 16, and 1 plus 6 is 7. 3 plus 3 plus 8 plus 2 is 16. 1 plus 6 is 7. 3 plus 0 is 3. 7 times 3 is 21. And 2 plus 1 is 3. And 3 plus 7 is 10. And 1 plus 0 is 1. So my final checksum is 1. But my value of 213,460 gives you 2 plus 1 plus 3 plus 4 plus 6 plus 0, which is 16, and then 1 plus 6 is 7. So I've clearly made a mistake. Looking back at my calculator, I can see I wrote 882, not 3382. What a fool I was. You might notice, though, that this is not a foolproof solution, because the chance of getting an error that randomly looks correct is only about 1 in 9. So some of the time it will tell you it's correct even if it's not, but it's still pretty good. In some ways, I feel I have made a foolish choice in trying to tell the history of mathematics by following the mathematicians, because much of the mathematics that we know and use now, or have known and used in the past, didn't necessarily come from a single known source. The history of mathematics, as told during doing the mathematicians, is like learning about the history of the Roman Empire by exclusively following the politics of the emperors. It's sometimes referred to as great man theory of history. Not because they're all men, and certainly not because they're all great, but the idea that history is defined by individuals. In contrast to this, we might look at a people's history mode of analysis. And that is, in part, what we're doing today, looking at the sorts of maths that ordinary people might have been using. If you want to learn about the Roman Empire, you might want to learn more about the people or their lives. What do they eat? What do they do for fun? How did their economy work? And what kind of jokes did they tell each other? Another approach to historiography we could use would be historical materialism. Trigger warning, this is the one favoured by Karl Marx. And this is where we identify the material tools and problems facing the people and identify how their history evolved with their interaction with these tools and problems. So ask yourself the question, why did the Roman Empire fall in the West? Was it due to poor leadership and the strong leadership of its enemies? Was it due to the Great Plagues that wiped out a third of the army? Or was it due to the shifting desires and allegiances of the clans consumed by the Roman Empire, seeking their own independence and identity? Or option D, all of the above. So I might suggest that the casting out of nines, or the double false position, comes under a banner of the people's history. These are the tools used by the merchant folk at the time period that we are discussing. And I might suggest that the translation of Greek astrology into Sanskrit by Yavanesvara comes under the banner of historical materialism, trying to solve the problem of accurately predicting events with astrology using better tools and implements. And for a refreshing change today, I don't really have a great man for you. Whoever Yavanesvara was, I'm sure he was a lovely bloke, probably more likely a man than a woman, but let's not pretend he changed history through sheer determination and will. Don't get me wrong, sometimes I think the world does change by an individual's sheer determination and will, and I will look forward to presenting a history on Euler, Erdois, Grothendieck, Noether, Germain. There are just so many great men and women to choose from. Or even next week, when we do come to another great man of Indian mathematics. We are getting closer to the Arya of genius. It's Aryabhata. And are we about to have a good episode? Yes we will. But before we go, let me thank you again for letting me tell this story of ancient mathematics. I must confess, I'm having a lot of fun researching in the Indian world. It's all new territory for me, and if it's new for you too, then welcome along for the ride. If you'd like to help support me make more episodes, please do check out my Ko-Fi page. The money is useful, but the encouragement is what really keeps me going. Or, of course, get in touch with me on BlueSky at Mathematicians-Pod. Until next time, goodbye. The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.